Ever looked up at the moon and wondered where it came from? For centuries, we had theories, but none of them quite fit. Some thought it was a captured asteroid, others that it was a chunk of the early Earth that spun off. But the truth, as we now understand it, is far more epic. A story of cosmic collision and rebirth. Let's travel back in time, about 4.5 billion years, to witness the violent birth of the Earth and Moon. Back then, our solar system was a chaotic construction zone. Dozens of planet-sized objects, called protoplanets, were zipping around, crashing into each other. Our own world was just one of these, a young, molten sphere we now call the. It was a hellish landscape of glowing rock and volcanic fury. Nothing like the blue marble we know today, but its destiny was about to change in the most dramatic way imaginable. Another world was on a collision course. Scientists have named this protoplanet Dea, after the Greek Titan, who was the mother of Selene, the goddess of the moon. Dea was no small asteroid. It was a planetary body roughly the size of Mars, a giant in its own right, and it was hurtling directly towards the proto-Earth. Imagine two worlds, each a swirling mass of molten rock and metal, about to meet in a cataclysmic embrace. The impact was unlike anything we can truly comprehend. It wasn't a simple crash. It was a planetary merger. Dea struck the proto-Earth at an oblique angle, a glancing blow of unimaginable force. The energy released was staggering, thousands of times more powerful than all the nuclear weapons on Earth combined. Both worlds were instantly vaporized at the point of impact, their crusts and mantles shattering and liquefying. This colossal collision threw a massive cloud of superheated rock and gas into orbit around the wounded Earth. Think of it as a Saturn-like ring, but not made of ice, made of vaporized planet. This debris ring was a churning, glowing halo of material, the combined remnants of both Dea and the Earth's outer layers. Now, gravity began its patient work. Within this scorching hot ring of debris, particles started to clump together. Small bits attracted other small bits, growing into larger rocks. These rocks collided and merged, growing into boulders, then into moonlets several kilometers across. It was a cosmic snowball effect, a rapid and chaotic assembly process. Over a remarkably short period, perhaps just a few decades or centuries, these moonlets coalesced into a single, large body. The moon was born. In its infancy, the moon was a very different sight. It orbited much, much closer to the Earth perhaps. 15 times closer than it is today. It would have loomed enormous in our sky, a giant, glowing bowl of molten rock. Its surface was a magma ocean, a sea of liquid fire. The gravitational pull between this newborn moon and the still recovering Earth was immense, creating colossal tides not of water, but of molten rock on both worlds. This theory, known as the giant impact hypothesis, isn't just a cool story. It's supported by solid scientific evidence. When the Apollo astronauts brought back lunar rocks, scientists made a startling discovery. The moon's composition is strikingly similar to that of Earth's crust and mantle, but it's severely lacking in iron. This makes perfect sense if the moon formed from the outer layers of Earth and Dea, while their dense iron cores merged together to become the core of the new, larger Earth. The collision also explains other long-standing mysteries. It would have tilted Earth on its axis, giving us our seasons. It also would have spun our planet up, dramatically shortening the day. In fact, early on, a day on Earth might have been only 5 or 6 hours long. Over billions of years, the moon's gravitational pull has acted like a brake, slowing Earth's rotation to the 24 hours we reused to and pushing the moon further away into its current, stable orbit. So, the moon isn't a sibling or a stranger. It's a child of the Earth, born from a cosmic collision. It's a piece of our own planet, blasted into space and reformed into the silent companion that graces our night sky. Every time you see it, you're looking at a reminder of our planet's violent, chaotic, and spectacular past. It's a testament to the fact that even from the most destructive events, something new and beautiful can be created. The Earth and Moon are forever linked by this shared, fiery history. I mean, look around us. Oceans, rivers, lakes, even the water inside you and me. It's everywhere, but our planet wasn't always this beautiful blue marble. Billions of years ago, Earth was a hot, molten mess. So, how did we go from a fiery rock to a water world? It's an epic story that involves violent volcanoes and visitors from outer space. Let's rewind the clock about 4.5 billion years. Imagine a young Earth, constantly bombarded by debris, with a surface so hot that any water would have instantly boiled away into space. The planet was essentially a dry, desolate wasteland. So, where did the first drops of water appear? Well, the first part of the answer might be bubbling up from deep within the Earth itself. Picture this. Early Earth was a volcanic playground. Volcanoes were erupting everywhere, spewing out not just lava, but also massive clouds of gas. This process is called volcanic outgassing. Think of it like the Earth letting off steam. And what was in that steam? A whole cocktail of gases, including water vapor. These ancient volcanoes acted like giant chimneys, releasing this trapped water vapor into the primitive atmosphere. As the Earth began to cool down over millions of years, something amazing started to happen. This water vapor in the atmosphere began to condense, forming thick, dense clouds that shrouded the entire planet. And then, the rain began. But this wasn't just any rain shower. This was a torrential, planet-wide downpour that lasted for, get this, possibly millions of years. Can you even imagine that? A continuous, global rainstorm for an unimaginably long time. This great deluge slowly filled up the basins and low-lying areas of the Earth's crust, giving birth to the very first oceans. It is an incredible thought. The water you drink today could have once been steam shot out of a 4-billion-year-old volcano. But hold on, the story doesn't end there. While volcanoes were certainly a huge contributor, many scientists believe they can't account for all the water we see today. The chemical signature of water from volcanic outgassing doesn't perfectly match the water in our oceans. So, there must be another source. And this is where our story takes a turn towards the cosmos. Let's look up to the sky. Billions of years ago, the early solar system was a much more chaotic place than it is today. It was like a cosmic pinball machine, with asteroids, comets, and all sorts of space rocks flying around and frequently crashing into the young planets. For a long time, scientists thought comets, which are essentially giant, dirty snowballs of ice and rock, were the primary water delivery service for Earth. It makes sense, right? A huge, icy comet smashes into early Earth, melts, and delivers a massive amount of water. It's a neat and tidy explanation. However, when we started studying comets up close, like with the Rosetta mission, we found a problem. The water on many of these comets has a different flavor than Earth's water. Let me explain. Water is H2O, but there's a heavier version of hydrogen called deuterium. The ratio of regular hydrogen to deuterium in water is like a chemical fingerprint, and the water in many comets we've studied has a much higher concentration of deuterium than the water in our oceans. It's like trying to say, a Great Dane and a Chihuahua are the same breed, just because they both dogs. The fingerprints just don't match. So, while comets definitely delivered some water, they probably weren't the main source. So, if not comets, then what? Well, let's talk about their rocky cousins. Asteroids. We used to think of asteroids as being mostly dry, barren rocks. But recent discoveries have completely changed that picture. We've found that certain types of asteroids, called carbonaceous chondrites, can be surprisingly rich in water. They're not big balls of ice like comets, but the minerals within their rock structure actually have water molecules locked inside them. These water-bearing asteroids formed in the outer part of the asteroid belt, far enough from the sun for water to be stable. Over time, the gravitational pull of giant planets like Jupiter nudged their orbits, sending them on a collision course with the inner planets, including our very own Earth. During a period called the Late Heavy Bombardment, about 4 to 3.8 billion years ago, Earth was relentlessly pummeled by these asteroids. It was a violent and destructive time, but it may have been the very thing that made life possible. Each impact from a water-rich asteroid was like a cosmic delivery truck, dropping off another shipment of precious H2O. And here, That's the really cool part. When scientists analyze the water found in these types of asteroids, its chemical fingerprint, that hydrogen to deuterium ratio, is a much, much closer match to Earth's ocean water. It's a voila moment for planetary science. It strongly suggests that a significant portion, perhaps even the majority, of our Planet S water was delivered from space by asteroids. So, it wasn't just one thing. It was a 1-2 punch. Earth had its own internal water supply, brought to the surface by volcanoes, creating a steamy atmosphere in the first rains. Then, for millions of years, it was pelted by water-rich asteroids from the outer solar system, topping up the newly forming oceans and delivering the final ingredients for the water world we know today. Think about that. The next time you take a swim in the ocean or drink a glass of water, you're interacting with a substance that has had the most incredible journey. Some of its molecules were forged deep inside our planet and erupted in ancient volcanoes. Other molecules traveled across the vastness of space for millions of years, locked inside a rock, before crashing down onto our world. It's a beautiful and complex story of how our planet became a home for life. The combination of geological processes from within and cosmic deliveries from without is what makes Earth so special. It reminds us that our planet is deeply connected to the rest of the solar system. We are, in a very real sense, made of stardust and asteroid water. What an incredible journey, right? From a fiery, dry rock to the vibrant blue planet teeming with life. It's all thanks to the dual forces of volcanic fury and an ancient bombardment from space. The universe is full of these amazing stories, and we're just beginning to piece them together. Have you ever stared up at a stormy sky, watched a bolt of lightning tear through the clouds, and wondered about its sheer, raw power? It's a spectacle of nature, both terrifying and beautiful. But what if I told you that this very same force, this chaotic electrical discharge, might hold the key to our very existence? What if lightning, combined with a little bit of chemistry, is what sparked the first life on Earth? It sounds like something out of a science fiction movie, right? A mad scientist, a dark and stormy night. But this isn't fiction. This is one of the most compelling scientific theories about the origin of life. And today, we're going to dive deep into the electrifying story of how we might have gotten here. To start, we need to travel back in time. Way, about 4 billion years ago. Picture the early Earth. A chaotic, volcanic world, shrouded in a thick, soupy atmosphere. No blue skies, no green fields, no oxygen to breathe. The air was a toxic cocktail of gases like methane, ammonia, hydrogen, and water vapor, all spewed out from constant volcanic eruptions. The oceans were a warm, primordial soup, rich in dissolved minerals. It was a hostile, alien planet, but it was also a planet brimming with potential, a planetary-scaled chemistry lab just waiting for a spark. And that's where the lightning comes in. The early Earth's atmosphere was incredibly turbulent, creating colossal, perpetual thunderstorms. We're talking about lightning strikes far more frequent and powerful than anything we see today. Each bolt of lightning is a massive jolt of energy. When that energy zapped through the primitive atmosphere, it did something amazing. It broke apart the simple gas molecules like methane and ammonia. Think of it like cosmic Legos. The lightning bolt shattered the stable molecular structures, leaving their individual atoms, carbon, hydrogen, oxygen, and nitrogen to float around freely. But these atoms didn't stay alone for long. They quickly rearranged themselves, forming new, more complex molecules. And among these new creations was something truly special: amino acids. Now, if you remember your high school biology, you'll know that amino acids are the building blocks of proteins. And proteins are the workhorses of life. They do everything from building our cells to carrying oxygen in our blood. Finding amino acids forming spontaneously in a simulated early Earth environment would be like finding the first brick needed to build a skyscraper. This incredible idea was put to the test in 1952 by two scientists, Stanley Miller and Harold Urey. Their experiment is now legendary in the scientific community. They built a closed system of glass flasks and tubes to mimic the conditions of early Earth. They filled one flask with water to represent the ocean and heated it to create water vapor. This vapor then mixed with the gases they thought made up the early atmosphere: methane, ammonia, and hydrogen. Then came the crucial part: the lightning. They zapped this mixture with continuous electrical sparks to simulate the constant storms. They let this experiment run for just 1 week. When they analyzed the ocean water at the bottom, what they found was astonishing. The clear water had turned a murky, reddish-brown. And swimming in that primordial soup were amino acids. Not just 1 or 2, but several different types of the very same amino acids that make up all living things on Earth today. The Miller experiment was a groundbreaking moment. It proved, for the first time, that the fundamental building blocks of life could arise from simple, non-living chemistry under conditions believed to exist on the early Earth. It showed that the transition from non-living to living wasn't a magical leap, but a series of plausible chemical steps. The spark of lightning really could have initiated the creation of life's essential ingredients. Of course, science is always evolving. Since the 1950s, our understanding of the early Earth's atmosphere has changed. Some scientists now believe it might have been less rich in methane and ammonia, and more dominated by carbon dioxide and nitrogen. But here's the fascinating thing. Even when the experiment is repeated with these new atmospheric models, the results still hold up. Electrical sparks still produce amino acids and other important organic molecules. Furthermore, we've found other potential sources for these sparks. It wasn't just lightning. Think about meteorites and asteroids constantly bombarding the young planet. The shock waves from these impacts could have provided the energy needed to forge complex molecules. Even the sun's intense ultraviolet radiation, unfiltered by an ozone layer, could have played a role. It seems that the early Earth was a dynamic and energetic place, with multiple pathways to create the chemistry of life. So, we have a soup, rich in amino acids. What's next? This is where the story gets even more interesting. These amino acids, floating in the warm oceans or collecting in tidal pools, would have needed to link together to form proteins. This process, called polymerization, is another critical step. Researchers suggest that clay minerals on the seafloor or evaporating water in lagoons could have acted as catalysts, providing a surface for these amino acids to meet, bond, and form long chains. Imagine a shoreline on the early Earth. Tides wash in, bringing a fresh supply of amino acids. The sun beats down, the water evaporates, and the molecules are concentrated, forced closer together on the clay surfaces. Over millions of years of these cycles, the first simple proteins, or proteinoids, could have formed. From there, the journey towards the first cell is still a matter of intense research and debate. How did these molecules learn to replicate themselves? How did they become enclosed within a protective membrane, forming the first protozoa? These are the next great questions in the science of life's origins. But what the lightning spark theory gives us is a powerful and plausible starting point. It provides a natural mechanism for creating the essential raw materials from which everything else could be built. It transforms the origin of life from an impossible puzzle into a question of cosmic chemistry. It tells us that life might not be an incredible fluke, but a natural, perhaps even common, outcome of the laws of physics and chemistry on a planet with the right conditions. The next time you see a flash of lightning, take a moment to think about it. You're not just seeing a weather phenomenon. You might be witnessing a modern-day echo of the creative force that 4 billion years ago zapped a lifeless planet and sparked the incredible, complex, and beautiful journey of life on Earth. A journey that ultimately led to you and me, sitting here, pondering our own origins. Hey Aberdeen, and welcome back to the channel! Have you ever looked up at the night sky, seen all those distant stars, and wondered, how did we get here? Not just us, humans, but everything alive. How did a barren, rocky planet like the early Earth transform into the vibrant, living world we know today? It's one of the biggest questions we can ask, and today, we're going on an epic journey. Back in time over 4.5 billion years, to uncover the incredible story of how life began. So, let's rewind the clock. Picture Earth, not as the blue marble we see from space, but as a fiery, chaotic world. We're talking about the Hadean, a name that literally means hell-like. Our planet was a molten ball of rock, constantly bombarded by asteroids and comets left over from the formation of the solar system. The atmosphere was a toxic mix of gases like methane, ammonia, and water vapor, nothing like the oxygen-rich air we breathe now. There were no oceans, no continents, just a global magma ocean. It was a hostile, seemingly impossible place for life to take root. So, what changed? The first major turning point was cooling. Over hundreds of millions of years, the planet's surface slowly radiated heat into space, forming a solid crust. As Earth cooled, the water vapor in the atmosphere began to condense, and then it started to rain. Not for a day or a week, but for thousands, maybe millions of years. This perpetual, planet-wide downpour filled the basins and craters, forming the first oceans. These primordial seas were not the salty blue waters we know. They were likely acidic and filled with dissolved minerals and iron, giving them a murky, greenish-brown color. But this water was the crucial ingredient, the solvent where the chemistry of life could finally begin. Now we have a stage planet with oceans, but we still need the actors, the basic building blocks of life. These are organic molecules, things like amino acids, which are the components of proteins, and nucleotides, which make up DNA and RNA. So where did they come from? There are two leading theories, and the answer is probably a mix of both. First, let's look to the skies. Remember all those asteroids and comets bombarding the early Earth? They weren't just bringing destruction. They were cosmic delivery trucks, analysis of meteorites that have fallen to Earth. Today, like the Murchison, shows they are packed with a rich variety of organic molecules, including dozens of different amino acids. It's mind-blowing to think that the ingredients for life may have literally fallen from space, seeding the young Earth's oceans with the necessary raw materials. Every impact, while catastrophic, could have been a delivery of potential. The second theory suggests these building blocks were made right here on Earth. Imagine the early Earth's environment. The lightning-filled skies, the intense ultraviolet radiation from a young sun with no ozone layer to block it, and the immense heat and pressure from volcanoes and hydrothermal vents on the ocean floor. This was a high-energy world. In 1952, the famous Milihori experiment tried to recreate these conditions in a lab. They took a flask of water with the gases thought to be in the early atmosphere, methane, ammonia, hydrogen, zapped it with electric sparks to simulate lightning. After just a week, they found that complex organic molecules, including several types of amino acids, had formed spontaneously. This experiment proved that, given the right conditions and a little energy, the building blocks of life could arise from simple, non-living chemistry. The early Earth wasn't just a stage. It was an active, planet-sized chemistry lab. Okay, so we have a watery planet, and we have the basic ingredients of primordial soup of organic molecules. But a soup isn't alive. How do you go from a random jumble of molecules to something organized, something that can replicate and evolve? This is perhaps the biggest leap in the story of life, and it's a puzzle scientists are still working on. The key problem is what's called the chicken and egg paradox. In modern cells, DNA holds the instructions to build proteins, but it needs proteins, enzymes, to replicate itself. So, which came first, DNA or the proteins? This is where a fascinating molecule called RNA comes in. RNA, or ribonucleic acid, is a bit like DNA's simpler, more versatile cousin. In the 1980s, scientists made a groundbreaking discovery. Some RNA molecules, called ribozymes, can act as enzymes. They can catalyze chemical reactions, just like proteins. But RNA, like DNA, can also store genetic information and replicate itself. This discovery led to the RNA world hypothesis. This theory proposes that the first life wasn't based on DNA and proteins, but solely on RNA. In this ancient world, RNA molecules could both store the blueprints for life and carry out the chemical work needed to build more of themselves. It neatly solves the chicken and egg problem. RNA was both the chicken and the egg. The first self-replicating entities might have been simple strands of RNA floating in the primordial soup, but a self-replicating molecule is still not a cell. To become a true living organism, you need a boundary, something to separate your internal chemistry from the chaotic outside world. You need a cell membrane. Think of it like a tiny protective bubble. These first membranes were likely made of simple fatty molecules called lipids. When you mix lipids with water, they naturally assemble themselves into hollow spheres, called vesicles. Or micelles. It's a simple property of physics and chemistry. If some of these self-replicating RNA molecules happen to get trapped inside one of these lipid bubbles, you'd have something truly special. A protocell. This was a revolutionary step. Inside this protective membrane, the chemical reactions of life could become more concentrated, more efficient, and more stable, shielded from the outside environment. This was the birth of the individual, the first ancestor of every cell and every living thing on Earth today. From these humble protocells, the first true life emerged. We call this organism Luca, the last universal common ancestor. Luca wasn't the first living thing, but it's the most recent ancestor that all life on Earth today, from the smallest bacterium to the largest whale. By studying the genes common to all three domains of life, bacteria, archaea, and eukarya, scientists can piece together a picture of what Luca might have been like. It was likely a single-celled organism, living in a hot, oxygen-free environment, probably near a deep-sea hydrothermal vent, feasting on chemical energy. It already had a complex system of DNA, RNA, and proteins, suggesting that the transition from the RNA world to the more stable DNA-based system we see today had already occurred. For the next 2 billion years, life remained simple, microscopic, and confined to the oceans. The world was ruled by single-celled organisms like bacteria and archaea, but one of these groups was about to change the world forever. They were called cyanobacteria, and they evolved a revolutionary new trick. Photosynthesis. They figured out how to use the energy from sunlight to split water molecules, creating energy for themselves. But this process had a waste product, a gas that was toxic to most other life forms at the time: oxygen. Slowly, over hundreds of millions of years, these tiny cyanobacteria pumped massive amounts of oxygen into the oceans and the atmosphere. This event, known as the Great Oxidation Event, was one of the most significant transformations our planet has ever experienced. It was a catastrophe for the anaerobic life that had dominated the planet, causing a mass extinction. But it also paved the way for a new, more complex form of life to evolve, life that could use this powerful oxygen to fuel a much more efficient metabolism. It's because of these ancient microbes that we have the oxygen-rich atmosphere we depend on. So next time you take a deep breath, think a cyanobacterium from 2.5 billion years ago. This new, oxygenated world set the stage for the final, incredible leap, the emergence of complex life. Around 2 billion years ago, a new type of cell appeared. The eukaryotic cell. This was a result of a process called endosymbiosis. The theory goes that a larger host cell engulfed a smaller bacterium but didn't digest it. Instead, they formed a partnership. The smaller bacterium, which was efficient at using oxygen to produce energy, became the mitochondrion, the powerhouse of the cell. A similar event with a photosynthetic bacterium led to the chloroplast in plant cells. Every complex organism today, including you and me, is made of these eukaryotic cells, a testament to an ancient act of cooperation between two single-celled organisms. This complexity allowed for the evolution of multicellular organisms, leading to the explosion of diverse life forms we see in the fossil record, from the first strange animals of the Ediacaran period, to the dinosaurs, and eventually, to us. And so, our journey is complete. From a fiery ball of rock to a living, breathing planet. From simple chemicals in a primordial soup to self-replicating RNA, to the first cells, and finally, to the vast and beautiful tree of life we see all around us. It's a story of chance, chemistry, and cosmic time. A story that shows how, under the right conditions, a non-living universe can give rise to something as wondrous and complex as life. Thank you so much for joining me on this incredible journey through time. If you found this as fascinating as I do, please hit that like button and subscribe to the channel for more deep dives into the biggest questions of science. Let me know in the comments what part of this story blows your mind the most. Until next time, stay curious. From the swirling chaos of the early universe, from a cosmic soup of dust and gas, something truly extraordinary emerged. Think about it. 4.5 billion years ago, our planet was a hostile, chaotic place. Then, against all odds, a spark ignited. Life. This wasn't a grand, sudden arrival, but a slow, painstaking process. Simple single-celled organisms, adrift in a primordial sea, were the humble beginnings of a story that would eventually lead to ... You. This is the story of evolution. The grandest epic ever told. It's the story of how chaos, through an unguided, relentless process, gave rise to order, to complexity, and ultimately, to consciousness itself. How did we get from simple chemical reactions to beings who can ponder their own existence, compose symphonies and gaze at the stars in wonder? Let's unravel this incredible journey together. Our story begins in the deep, dark oceans of ancient Earth. The first life forms were incredibly simple, barely more than self-replicating molecules, protected by a fatty membrane. For billions of years, life remained microscopic, but beneath the surface, a silent revolution was underway. These tiny organisms were competing, adapting, and changing. A crucial currency in this ancient world was energy, and the ultimate energy source was shining right above them. The sun. The evolution of photosynthesis was a game-changer. Organisms like cyanobacteria learned to harness sunlight, releasing a waste product that would forever alter our planet. Oxygen. This great oxidation event was catastrophic for much of existing life, but it paved the way for a new, more energetic form of metabolism. It was this oxygen-rich atmosphere that allowed for larger, more complex life forms to evolve. It's a powerful reminder that sometimes what seems like a disaster can be the very catalyst for the next great leap forward. With more energy available, life could afford to get more complex. A pivotal moment was the emergence of eukaryotic cells, cells with a nucleus and specialized compartments called organelles. One theory, endosymbiosis, suggests this happened when one simple cell engulfed another, and instead of digesting it, they formed a partnership. That little engulfed bacterium became the mitochondria, the powerhouses of our own cells today. This cellular teamwork allowed for an explosion of diversity. Cells began to clump together, forming multicellular organisms. At first, they were simple colonies, but soon, cells started specializing. Some became skin, others muscle, and some ... nerve cells. This was the dawn of the nervous system. The first nerve nets were simple, allowing creatures like jellyfish to react to their environment. In a basic way, it wasn't thought, it wasn't feeling, but it was the first step towards processing information about the outside world. It was the moment life began to not just exist, but to sense. This new ability to sense the world sparked an evolutionary arms race. As predators evolved better ways to find prey, prey evolved better ways to escape. This constant pressure drove the development of more sophisticated sensory organs and more complex nervous systems to process the incoming information. We see the emergence of bilateral symmetry, a body plan with a distinct head and tail. And where do you put the command center? At the front, of course. This process, called cephalization, led to the concentration of nerve cells and sensory organs at the one end of the body that encounters the environment first. This early bundle of nerves was the precursor to the brain. In creatures like the flatworm, we see the first primitive brain, a simple ganglion that could process information from its two light-sensitive eyes. It could tell light from dark, helping it find food and avoid danger. This was the humble beginning of the organ that would one day write poetry. As animals moved from the sea to land, the challenges became even greater. Gravity, dehydration, and vast temperature swings demanded new adaptations. And with every new challenge, the brain evolved. The brain of a reptile, for instance, is brilliant at regulating basic survival functions: breathing, heart rate, and the classic fight-or-flight response. This reptilian brain still exists within all of us, the ancient core that keeps our basic machinery running. Then came the mammals. With their warm-blooded metabolism and nurturing behaviors, a new layer evolved: the limbic system. This is the seat of emotions, of bonding, of memory, and of play. It allowed for social structures, for parental care, and for a richer, more emotionally complex experience of the world. It's why you feel a rush of affection for a puppy or a sense of comfort from a friend's hug. This wasn't just about survival anymore. It was about connection. And then, the final, most recent addition to our cranial architecture. These ranniculi, outer layer of the brain, is most developed in primates, and especially in humans. This is the home of our higher cognitive functions. It's where logic, reason, and abstract thought happen. It's the part of the brain that allows us to use language, to plan for the future, to understand complex mathematics, and to create art. The incredible folding of the neocortex allows us to pack an enormous amount of processing power into a compact space. This expansion of the neocortex, particularly the frontal lobes, is what truly sets us apart. It's what enables us to build civilizations, to develop technology, and to ask the very question we're re-exploring today. How did we get here? Our brains are not just one single thing, but a beautiful layered history of life on Earth, from the basic survival instincts of a reptile to the emotional world of a mammal, all topped with the extraordinary reasoning power of the human neo. So, we have this 3-pound universe inside our skulls, a product of billions of years of trial and error. But where does consciousness fit in? This is one of the deepest mysteries in all of science. Is consciousness simply an emergent property of a sufficiently complex network of neurons? A bit like how a wet feeling emerges from the interaction of H2O molecules, which aren't individually wet themselves. When billions of neurons fire in intricate patterns, does self switch on? This is the idea of emergence. Consciousness isn't a thing located in one spot, but a process, a symphony played by the entire orchestra of the brain. It's the brain's way of creating a unified, coherent model of the world, and placing a self at the center of it. This user illusion is incredibly useful. It allows us to navigate a complex social and physical world, to make plans, and to understand that other beings have minds of their own. Think of it this way. Evolution doesn't have a goal. It's not trying to create consciousness. It just favors whatever works, and having an internal model of reality, a sense of self, and the ability to predict the future turned out to be a massive survival advantage. A creature that can remember where it found food, anticipate the actions of a predator, and communicate its plans to others is far more likely to survive and pass on its genes. Consciousness, in this view, is the ultimate tool for survival. It allows us to move beyond simple, pre-programmed instincts and to respond to novel situations with flexibility and creativity. It's what allowed our ancestors to craft better tools, to build stronger communities, and to spread across the entire globe, adapting to every environment they encountered. From the chaotic dance of molecules to the intricate firing of neurons, the journey to consciousness is the story of matter waking up and becoming aware of itself. So, what does this all mean for us? It means that we are living, breathing history. The salt in our sweat is a relic of the ancient oceans. The structure of our brain tells the story of every evolutionary struggle our ancestors faced. We are the current peak of a 4-billion-year-old process that turns stardust into storytellers. It's a humbling and awe-inspiring thought. We are not separate from nature. We are its most complex expression. We are chaos, organized and aware, and the story isn't over. Evolution continues, and who knows what forms consciousness might take in the future. But for now, we have this incredible gift, the ability to experience joy, to love, to create, to learn, and to wonder. The ability to look back at the chaotic origins of the universe and see the long, winding path that led to this very moment. That, in itself, is a miracle born from chaos. Thank you so much for joining me on this incredible journey through time.